It's light in blue. It journeys across the universe, it stretches, it stretches, it stretches. It moves towards the red bit of the spectrum because it gets stretched. And so you see the whole fingerprint of the atoms moved from the blue bit of the spectrum to the red as the light gets stretched, as space stretches. That's what we observe. So that's a very direct measurement that tells us that the universe is expanding. That's one piece of the puzzle. So just qualitatively you can say that tells us our universe is stretching, space itself is stretching. When you get into your car and you set a satellite navigation, the satellite navigation system works basically by measuring time differences between clocks on satellites and clocks on the ground. The satellites are moving relative to the ground and they're high up, so gravity is a bit weaker. Turns out that means time passes at a different rate. How much? Well, Einstein predicted 100 years ago that it would shift by 36,000 nanoseconds per day. A nanosecond is 1,000 million for the second. That doesn't sound like very much, but light travels 30 centimeters in a nanosecond. So that means that the satellite navigation system would drift by 36,000 lots of 30 centimeters in its position measurement. It's about 10 kilometers. So the satellite navigation position would change by 10 kilometers a day if you didn't take account of that, which Einstein works out in 1905 by thinking about a light clock with two mirrors. This is a picture of perhaps 1 billion stars in the center of this galaxy shining brightly. This looks like a star that must be closer to us than that galaxy because it's so bright. It actually isn't. It's actually something called a supernova explosion. This is a star in the galaxy. It's on the edge of the galaxy. It's the same distance away as the 1 billion or so suns in the center and the 100 billion or so stars in the disk. Same distance away, but it's going as brightly as 1 billion suns. How could that be? One star glowing as brightly as 1 billion? Well, it's the ultimate fate of the sun. It's a star that's burnt out all its fuel and is just sitting there in space, gradually fading away. But it's a white dwarf that had a companion star orbiting around it. Now, the white dwarf, the dying star, sucks matter off the companion star until it gets too big to support itself, and then it collapses and it explodes.
Does the Big Bang disprove the existence of God? No, it's kind of the opposite actually, isn't it, in some sense, because historically, Georges Lemaitre, who's often described as the father of the Big Bang, was a priest as well as a mathematician, and he was delighted that Einstein's theory certainly appears to suggest that there could have been a beginning. Einstein didn't like that, he wanted the universe to be eternal, but Einstein's theory is strongly suggestive of a beginning or an end, and Lemaitre as a priest was happier with that, because if you think about what a beginning is, you could call it in that language a moment of creation. Should we try to save the Earth instead of trying to get off it? It's really important to say that nobody I've spoken to, and certainly my opinion, you don't try and go into space and up to the moon and Mars and build space stations and so on so you can escape the Earth when you've messed it up. It is the opposite. The idea is that by going into space, building infrastructure, accessing resources in space, and all the good things you can do in space, drug development, developing semiconductors, all sorts of industries that we can imagine in Earth orbit, you save the Earth because the Earth is the best place in the universe because we evolved on it and it's unique. The idea of going into space is not to mess the Earth up and then escape it. It is exactly the opposite. I was involved in a discussion yesterday. One of the experts in the space economy said to me that really we shouldn't think of the space economy as space. We should think of it as the economy because it's not far. Right? It's just 100 miles up there. We're in London now, so it's about the distance from London to Birmingham. If you go from London to Birmingham, but you go that way, you end up somewhere where you can do stuff that is useful and it can produce economic growth. It can produce things like interesting drugs, for example, medicines and things which are not easy to build on Earth and so on. You should think of space now, not as a thing, a separate thing, but as a place where there's an opportunity to do stuff that benefits us all here on Earth, and that's the challenge. Why is time different on different planets like in Interstellar? As you come closer to a planet, let's say you have a watch and you look at the watch, then you'll see the watch tick at the normal rate, 1 second per second, and you won't see anything unusual. But from the perspective of someone far away, that watch will be ticking more slowly than their watch. And it's really to do with the distortion of space and time in the vicinity of the planet. So the general rule is if you go to something that's very massive, you approach a very massive planet or even a black hole, then as you go there, from the point of view of someone far away, they will see your time tick more slowly. That's basic general relativity. That's what everybody should know. Is time travel possible? It's kind of obvious to say it's possible into the future. Pete, if you look at where you've got to, and you say, well, that's okay, then I don't think it's too complicated, isn't it? I don't think you can unpick things. I don't, So I don't think in those terms. I don't think I wish I hadn't done that. I mean, there's always things, and sometimes there can be serious things, and we say, I wish that was a mistake. But you get to where you are, and I think you have to accept the fact that your history is the history that.
So you don't do regret or anything like that?
No, I mean, but then again, you have to be careful with those things. I mean, I'm lucky that I haven't done anything that I really, really, really had to regret. Then someone will go on Twitter through my Twitter history and go, look at that.
Yeah. There's that trick suit.
Yeah.
What is your biggest weakness? What is your greatest strength?
That's a good question, isn't it? Because I don't feel comfortable answering either of those questions because I haven't thought about it really. So weakness, I mean, it probably. I mean, I do find it hard to make decisions, which everyone who works with me professionally, especially people who are on the kind of more admin side of my world, say, God, can you just make your mind up? I do tend to, especially difficult decisions, I tend to push away. I don't want to annoy people. So I don't want to disappoint people. So I do have this tendency to go, actually, I'm not going to do that, but I'm going to tell them tomorrow. And strength, I think it probably, you mentioned optimism. So I tend to be optimistic that there'll be something interesting to do.
Yeah.
I'll find interesting things that interest me, new learning curves. So I tend to be quite optimistic. And again, some people that know me say that it's a flaw because it's probably maybe overly optimistic. But I think it's a strength.
Nice.
Sense of possibility.
What do you think people most commonly get wrong or misunderstand about you?
It was funny. I got asked, a government department asked me to go in and have a chat with them about something. And I think they expected to have this nice bloke off the telly who's just going to go, it's great, the stars are nice, aren't they? Robin Ince, my friend, is a great, look at that shiny light in the sky. And then that's it, that's me, right? They're shiny, nice, big smile. And of course, I kind of piled in on them on something about higher education policy, whatever it was, and I had some facts which threw them somewhat, some data. So look at this, and it was about, and in the end, and I didn't get asked back, and they said that I got this years later. Actually, someone said to me, there was this word went round that you're intellectually aggressive.
Oh wow!
Right, so they didn't want me in the room, and so I think sometimes people think that I'm very, 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 very nice. Like I just sit there and look at the sky and think nice thoughts. But of course also, I was trained, as an academic. That's what I did, physics. And it's as we said earlier, it's quite a brutal profession. It's you're trying to get to the bottom of how nature works. Yeah. And so there's not a lot of room for just sort of floating around being nice. You're trying to understand stuff. So I think it takes people by surprise. Sometimes if someone's asking me in a private setting, for example, for some opinion on education policy or whatever it is, then sometimes it takes them by surprise that I'm not quite as fluffy and nice as they thought.
I don't believe it. I think it's lovely. We have a high performance book club. We've got tens of thousands of members. They love discussing books on there. Obviously you can't mention your own because that's against the rules. But what would be the book that you would love to throw into the mix for the high performance book club?
There's a couple of books by a great physicist friend of mine called Sean Carroll that I really like, on the origins of life, meaning of the universe itself. It's called The Big Picture by Sean Carroll, and it's a really great sort of wander through a lot of the things we've spoken about actually today. So I think that's a very good book.
Lovely.
He had another great book, which is a bit, but also it's called Something Deeply Hidden, and it's one of my favourite quotes. And I do it in my live show actually. It's an Einstein quote. And as Einstein said, that if you pay attention to nature, really and pay attention and keep going and try to understand something and keep pulling the intellectual threads, everything we've spoken about today, if you do that and you're persistent and also lucky and fortunate, there's a chance that you can catch a glimpse. So you could say, well, okay, so what happens if we stay here? We become a spacefaring civilization. We don't destroy ourselves, or we aren't destroyed by some impact from space. Then could you conceive of technology that could start to affect the solar system? And the answer must be yes. We could imagine building cities on Mars. We could imagine, in physics, pure physics terms, terraforming Mars, turning it into a habitable world. We could imagine going to the moons of Jupiter or Saturn. We could imagine going to the edge of the solar system. You could even imagine, could you imagine technology in 1 million years, let's say, that would allow us to begin to affect the lifetime of the sun? Could you imagine that? In physics terms, according to laws of physics, I suppose you could. You could imagine a tremendously powerful civilization that could start to, I don't know, throw material into the sun, whatever it is. Maybe it was a ridiculous thing to do, but you could at least imagine it. And then you go 1 million years, 2 million years, 3 million years, 10 million years, 1 billion years into the future. Imagine that our civilization expands to the stars and becomes an interstellar civilization. Imagine our civilization populates the entire galaxy. There's nothing in the laws of physics that prevent that. And imagine we start to understand the quantum theory of gravity. We start to understand how space-time works. Imagine if we start to glimpse some underlying structure in reality that gives us power that we've not yet dreamed of. Who knows in 1 billion years? And so is it really true that in the far future of the universe, then life will play no role? Or could it be that life could play a central role in the far future of the universe? And the reason that it reminded me of Barrow and Tipler's magnificent book, The Anthropic Cosmological Principle, which I strongly recommend, is that in there they consider a cosmology, which is, it sounds like science fiction, but you can conceive of it given the known laws of nature. It's a cosmology called the omega point cosmology. So they consider a recollapsing universe. Now, at the moment, our universe is accelerating in its expansion, or whether it continues to do that forever, we don't know. But at the moment, there it is. But in a recollapsing universe, you can at least consider a situation where life in the far future is so powerful that it can begin to control the collapse of the universe and try to configure it, presumably by moving matter and energy around in some inconceivable way. You can just about construct this thing such that the ability of life to process information increases faster than the rate of collapse of the universe. And so what that means, what does it mean? It means that what's the appropriate measure of time for an intelligent being? It's really, I think fundamentally, it should be considered, you should think of it as the time it takes to process one bit of information. And it turns out that you can at least write the equations down for a universe in which the ability to process information diverges to infinity before the universe collapses. So you in that case, you almost say that life manipulates the universe such that it becomes immortal, right, in the far future. Now, I emphasize, this is complete, it's beyond speculative. So I'm not advocating for this, for this position that that's the way that nature is. But it's really interesting. It was really interesting to me to just think about it. The point, I think, the key point, which is interesting, is that it's not necessarily the case that life remains insignificant on a cosmic scale. You shouldn't assume that, because if life persists sufficiently long and becomes sufficiently knowledgeable and powerful, then it may be able to influence larger structures, not just planets and not just solar systems, perhaps not just even galaxies. And it's a very beautiful idea.
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.
But actually what it is a measurement. And at the moment, our measurement is, given what we measure, then it's 10 to the minus 35 meters. But you could imagine configurations of the universe where it's rather bigger than that.
What kind of insights does the Planck scale reveal?
Now, the Planck length, this unimaginably small number in meters, you might say, well, how does that affect our everyday lives, right? Does it come into any calculation of a thing that we can conceive of? And there is a beautiful calculation. It's one of my favorite calculations in all of physics that was initially done by the great mathematical physicist Chandrasekhar back in the 1930s. And it's a stunning calculation. It's about the mass of white dwarf stars. So let's think about a white dwarf star. What is that? So what is a star, first of all? So a star is some material, it's mainly hydrogen and helium, collapsing under its own gravity. So gravity is trying to squash this thing down. What holds it up? Well, as the star contracts, as it forms, our sun formed around 4.5 billion years ago through this process, the gravitational collapse. That means the core heats up, and it heats up, which means that the hydrogen and the helium is driggling around very fast, and ultimately you switch on nuclear fusion reactions in the core. And the fusion reactions, in the case of our sun, hydrogen is fused into helium that releases energy, which creates a pressure which holds the star up. So the star's a balancing act. Gravity is trying to squash it, heats the core up, fusion reactions release energy, creates a pressure, holds it up. But of course that doesn't exist, it can't carry on forever, because the star doesn't have an infinite amount of fuel in its core. And so ultimately we'll run out of fuel and it will begin to collapse again. And then stars will start to fuse heavy elements and so on. But ultimately, you could ask the question, well, when there's no more nuclear fusion can occur in the core, what happens to the star? Does it just collapse without limit, which would be a black hole as we now understand it? Or is there something else that can hold it up, some other property of matter? This wonderful calculation is a calculation about what happens to electrons in a collapsing star. So it's a genuine quantum mechanical calculation. So what happens? One of the properties of the universe, one of the fundamental ideas in quantum mechanics, is called the uncertainty principle, Heisenberg's uncertainty principle. So it says that if you try to confine an electron into a smaller and smaller box, which means you're trying to measure its position, right? You're trying to confine it and squash it down, then the product of the size of the box, the uncertainty in the position, multiplied by the uncertainty in the momentum of this thing, has to be greater than Planck's constant, fundamental property of the universe. So as you try to, this star's collapsing and all the electrons are getting pushed together and closer together, they try to avoid each other, which is another fundamental property of quantum mechanics called the exclusion principle, which roughly speaking says they don't like to be in the same place, roughly. And so you start to squash them. They try to get away from each other. They go into little boxes in the star, and the boxes are shrinking. And so the electrons are getting confined, and so they jiggle faster. The uncertainty on their momentum is faster and faster. And so they start to jiggle around because they're getting squashed into each other and trying to stay away from each other. So this is pure quantum mechanics. The uncertainty principle, the Pauli exclusion principle, jiggling around. That jiggling is like a temperature in a sense. It creates a pressure which can hold the star up. So you could do the calculation, but what happens is I squash this down and the electrons start to jiggle more, they make the pressure, they hold the star up. What happens if that jiggling starts to bump into relativity? What happens if it starts to go towards the speed of light? They can't jiggle any faster. And so ultimately there must be a limit on the pressure that these electrons in this quantum mechanical process can exert to hold this thing up. So you can do the calculation, and it's done. I did it in a book called The Quantum Universe. There's a gratuitous bit of advertising. It's in the appendix. So you can do it. It's not a hard calculation. It's some details are difficult, and Chandrasekhar did this magnificent calculation. If you do that calculation, you find that the maximum mass of a star which is just a lump of matter held up by this process, is 1.4 times the mass of our sun. So it's an astonishing calculation. How does that relate to the fundamental properties of the universe? Because all we've used there, we've used quantum mechanics, and we've used the strength of gravity. Those are the things. These are the things. Planck's constant, the speed of light, Newton's gravitational constant. Those are the things we used when we looked at the Planck units, like the Planck length. So you can use those things, strength of gravity, speed of light, Planck's constant, to construct a mass. It's called the Planck mass. And it's rather big, actually. So whereas the Planck length is very, very tiny, the Planck mass is about the mass of a grain of dust, a mote of dust. It's quite a large thing. But you can calculate it. Fundamental property of the universe, using Newton's gravitational constant, speed of light, Planck's constant, comes into that calculation. Turns out, when you do the calculation, that roughly speaking, that number, the Chandrasekhar limit, is the Planck mass cubed divided by the proton mass squared. That's what it is. You do that calculation, put the numbers in, it's about 1.4 times the mass of the sun. But I find it profoundly important. It's a beautiful, beautiful result. Because what we're saying is that you can calculate the maximum mass of a load of stuff that can hold itself up through this quantum mechanical process. And it just depends on these fundamental properties of the universe. Strength of gravity, Planck's constant, speed of light. That's it. So it's a very, very beautiful calculation. But it's the best example I know of the relationship between these rather abstract quantities, perhaps, and something that you can look at in a telescope. It's a beautiful piece of physics.
How does our comprehension of scale break down?
So we have this fundamental, it appears, length scale in the universe, 10 to the minus 35 meters, a Planck length, unimaginably small. How could you picture that? Well, take a proton. So a proton is pretty unimaginably small, I think, to most people, although it's pretty big in particle physics terms. We have maps of the interior of the proton, the constituents of the proton, that we use in particle physics experiments. So it's kind of a big world, a proton. But if you take a proton and expand it to the size of our solar system, so imagine that, the nucleus of a hydrogen atom, and you imagine expanding that to the size of our solar system out to the orbit of Neptune, then something that's the Planck length would extend or expand to, let's say, a virus or a living cell. So the ratio in size between the Planck length and a cell, which we can just about see under a microscope, is the same ratio as a proton to the solar system. So it's unimaginably small. So we can just about conceive of the size of a living cell. And then where does our picture of the universe start to break down? Of course, the things we can really get a feel for are things that are around, let's say, a few inches, a few centimeters to a few meters, or maybe if you're a runner, you get a sense of what a few miles means. But I think it's quite difficult to even picture. I suppose 100 miles you can picture because you can take a train ride, or a few thousand miles you can picture because you can get on an aircraft and fly across the Atlantic. So we have a kind of a picture of that. But when you get much bigger than that, we don't experience those distances anymore. So I would say that when we start to talk about distances that are much larger than distances that we might travel on the surface of the Earth, then I think our feel for those distances begins to break down. Maybe if you spoke to Buzz Aldrin, then he would have a feel for the distance 250,000 miles because he's flown it right to the moon. So maybe the Earth to the moon. But then when you start to talk about the distance to the planets, or the distance to the sun, the so-called astronomical unit, 93 million miles. What does 93 million miles mean? I suppose you could get a feel for that by looking at the sun in the sky, not directly, I'll say, don't look at the sun, but you know what I mean? We know kind of at the sunset, let's say, when you see that disk of the sun. And so you can see it's the same size. It's very easy to do safely, actually, because it's the same size on the sky as the moon. So look at the moon. The moon is the same radius on the sky as the sun. You know that because of total solar eclipses. It is a coincidence based on the way that our solar system has evolved, but it's a nice coincidence. So we can perhaps conceive of what the sun looks like on the sky, 93 million miles away. You can fit 1 million Earths inside the sun. So how do we conceive of that? The radius is something like 100 times the radius of the Earth. That means that if you got in a passenger aircraft, and so we have a feel for that. You can fly from London to New York, you know how long that is, a few thousand miles. What does that diameter of the sun mean? Well, it'd take something like months, I think something like a year, to fly around the sun in a passenger aircraft. It becomes inconceivable. And the sun's quite a small star. So then we start to think of bigger distances. So the most distant object that we created, we built, the Voyager 1 spacecraft, is now well over 150 astronomical units from the Earth, 150 times the distance from the Earth to the sun. What does that mean? It takes light over 22 hours to reach it. So a signal at the speed of light. And that's just about, by some definition, the edge of our solar system. Although actually, if you talk in terms of these icy objects in what's called the Kuiper Belt and the Oort cloud, it's really not the edge of our solar system at all. We think that extends maybe a light year out into the universe, the radius of the sun's influence, if you like. A light year, so 22 hours, just about a day for light to go to the most distant object we are in communication with, which has been flying since the 1970s, right, on its way out. One day, a light day, basically. And then we have 365 times that, a light year, which is to the frozen edge of the sun's influence, the edge of the Oort cloud. 4 times further than that, you get to the nearest star, the Proxima Centauri, the Alpha Centauri system. That star about 4 light years away or so. So that's inconceivable. Light traveling at 186,000 miles a second, 186,000 miles a second, 4 years to the nearest star. And then you start to talk about a galaxy then, the Milky Way galaxy. We're all in orbit around the center of the Milky Way galaxy. How big is this collection of stars? Somewhere between 200 and 400 billion suns in the Milky Way galaxy, about 100,000 light years across. And that's a fairly typical size for a large galaxy. One galaxy, one island of stars, 100,000 years for light to cross it at 186,000 miles per second. And then you say, well, what about the nearest galaxy? So you go outside on a clear night where there's no moon and it's dark, away from the city lights. And if you know where to look, you can just about see our nearest neighbouring large galaxy. It's called the Andromeda Galaxy. It's a bit bigger than the Milky Way, but give or take, let's say 100,000 light years across or so. Maybe double the number of stars, we think, in the Andromeda Galaxy. That galaxy is 2.5 million light years away. It means that the light is worth looking at. It's a beautiful thing to look at, because it means the light entering your eye began its journey before we had evolved on Earth. It took 2.5 million years to reach us. But you can see it with the naked eye because it's so big. It's very faint. You can certainly see it with binoculars, but it's about the diameter of a full moon on the sky. And that's 2.5 million light years away because it's a big thing. And then you start to say, well, what about the other galaxies? So we've measured galaxies now out to what we close to the edge of the observable universe with instruments like the James Webb Space Telescope, from which the light has journeyed for over 13 billion years to reach us. 13,000 million years to reach us. And the universe has been expanding later, but it can be in a state where it could be 30% heads and 70% tails, or 40% heads and 60% tails, or any combination, any mixture of heads and tails. And that is a perfectly legitimate description of the state of the configuration of this thing. Just to give you a sense of a real physical object that would behave that way, particles like electrons, for example, have a property called spin, which can be up or down. It's like heads and tails. But that's the key thing, that objects like electrons can not only have definite values of some property, something that you can measure, but they can be in a mixture of those things. And it's not a probability theory in the sense that we would usually think of probability theories. So usually we'd say, well, there's a 50% chance it's going to rain tomorrow. Why do we say that? Why we would say such a thing is because we have incomplete knowledge of the system, in this case the weather. And so we have incomplete understanding of where, I suppose at the most basic level, all those water molecules are in the clouds and so on. But we don't have enough knowledge to precisely calculate what is going to happen. And so we assign probabilities to it, which that reflects our ignorance of the situation. The key difference in quantum theory is that these probabilities are fundamental. They are fundamental to the description of nature. So it is not the case that if we have an electron in some kind of configuration, then our theory predicts probabilities because we don't quite know exactly how this thing is configured. The probabilities are intrinsic to the theory itself. And pretty much all of the intellectual challenges and the confusion around quantum mechanics comes from that very simple property.
What is the double slit experiment?
If you look at pretty much any book on quantum mechanics, there is one experiment which you can describe. It's a very simple experiment which encapsulates all the I was going to say weirdness, but it's all, let's say, all the properties of the quantum world. It's called the double slit experiment. And by the way, I'll strongly recommend, I think it's almost universally accepted, the best description of the double slit experiment is freely available. It's in the Feynman Lectures, Volume 3, first chapter. And I've read quantum mechanics textbooks that say, go away and read the first 2 chapters of the Feynman Lectures on Physics, Volume 3, because it's all in there. Can't be done any better. So I could recommend that if you find this interesting. The double slit experiment is essentially, let's say you have something that will emit, let's say electrons, so particles, electrons, electron gun that emits particles. And then you have a barrier that has 2 slits cut in it and a screen. So that's the setup of the experiment. So we have something that emits electrons, 2 slits cut in a screen, and a detector, another screen that the electrons will hit. So you fire the electrons out. So what will that look like? Well, if you think of the electrons as just little particles, little bullets, let's say, that are emitted from this gun, then you would imagine that the electrons can go through one slit or the other one, depending on how they come out. And you can imagine that they might get deflected around a little bit when they go through the slits. But basically, on the screen, you would expect most of the electrons to appear opposite one or the other of the slits, with maybe a bit of a spread because they rattle around a bit when they go through. So you get lots here, and pretty much none in the middle. But that's not what you see. What you see is a very clear pattern on the screen. You see sort of stripes, a stripe on the screen where you get lots of electrons, and then a stripe where you get very few or none, and then another stripe where you get lots, and then a stripe where you get very few or none, and then another stripe, and then very few or none. So you get this stripy pattern. That pattern is exactly the same pattern that you would get if you sent waves through the slits. Let's say water waves, any kind of waves. Then it's easy to understand. Because what's happening then, and physicists knew this back in the 1700s, right, is that you can consider each slit as a source of new waves. And the waves come out, and waves have the property that they can interfere with each other. So you can get the peak of one wave arriving at the screen from one slit, and a trough of a wave arriving at the screen from another slit. And if everything's lined up correctly, the peak and the trough cancel out and you get nothing. So you get this property where something from each slit, it's very easy to understand if it's a big extended wavy thing, lines up in such a way that it cancels out. And then it could line up in such a way that it reinforces, and you get a big disturbance there, and then it cancels out again, and then it reinforces again. So you can imagine this stripy pattern on the screen. That's what you get with waves. The fact that you get it from particles is interesting. But here's another interesting thing. You still get that pattern if you send one particle at a time through the slits. So it is, and let me use my language carefully, I was going to say it is as if the electron can somehow explore both paths, just like a wave can, and then interfere with itself to control where it lands on the screen. As if is something that people might object to. Many physicists would say, no, it does. So the statement is that the electron explores both routes at the same time, at once, let's say, on its route from the electron gun through the slits to the screen. So that's a very strange picture of reality. We surely think of particles as following definite paths. And it might be that you don't know quite which path it's going to take, but surely you would say, in reality, it will go one route or the other route. But that experiment, which I emphasize has been done now many times, tells us that nature is not like that. It tells us that the electron must, in some sense, explore all routes on the way from the gun to the screen. And so the question then becomes, well, what do I mean by in some sense? What you'll see in the Feynman lectures is he gives you two pictures of how to think about physics. One is he gives you the way that you would calculate what you're going to see on the screen. And that's really simple, as Feynman points out. So what you can do is you can calculate what's called a complex number for every route that the particle, the electron, can take from gun through the slits to the screen. So every route, every path it can possibly take. A complex number, for those that don't know about complex numbers, can be pictured as a little clock face. So a complex number has a clock hand, there's a length of the clock hand, and there's the time on the clock face. And you can calculate how those clock faces kind of evolve and change and spin around from the moment the electron's emitted to the moment it hits the screen. And the prescription is very simple. You can calculate what those clock faces look like, what those complex numbers are, and at every point on the screen, you have to take them all, every possible path to that point, and just add them up. And the length of the clock hand gives you the probability to find the electron there. It's actually the squared length of the clock hand, but whatever, it's the length of the hand. That's it. So you can see that you have this property, you can have interference, you can have one clock arriving at 12 o'clock and one clock arriving at 6 o'clock and they cancel out and so on. You just do that, you calculate it, and you get the right answer. So it's a very, very simple prescription. But I suppose the problem comes when you say, well, what does it mean? Does it really mean, is this just calculation, or is this just mathematics? Or does it really mean that the electron explores every possible route? And by that, I mean every possible route. You might consider it going to the Andromeda Galaxy and back, right? Every possible route on its journey from when it's emitted to when it's detected. And I think many physicists now would say that that is a correct description of reality. The particle does. But I just want to emphasize that the mathematics, the way that you make the calculation, is pretty simple. It's a prescription for making a calculation and you get the right answer to the experiment. The problem with quantum mechanics, I suppose, is what when you try to interpret what the calculation means for the nature of reality. I think it's important to say that there aren't different rules of the game in the subatomic world and the world that we observe, this world of common sense, let's say, that we perceive. There aren't different rules. And it's pretty well understood, I would say it's well understood, how the world that we see emerges from this rather strange but well-defined behaviour that we see in the subatomic world. And it's not only the subatomic world, by the way. This is now, maybe you could have argued 50 years ago that this is just all philosophy, it doesn't really matter, whatever. But now we have an increasing number of quantum technologies that are really based on this behaviour, the quantum computers being a good example. And so you see that this is not just something that you can say, well, we don't need to think about it really because it's in the world of atoms and it's all a bit whatever, and we can just do some calculations, because we're using that behaviour now in technologies. And so it really does become an important theory to try to understand.
Why is it important that we seek to solve the mysteries of quantum physics?
Now, you go back a few decades, then I think you could say that the interpretations of quantum mechanics are very interesting and very important because we're talking about the nature of reality. But you might say, well, it doesn't really matter so much practically, right? Now, I have a lot of colleagues in physics who would, I think rightly, hate that description because what we're trying to do is understand reality, what physics is. But now, particularly I think, with the possibility of building quantum computers, this attempt to understand how large systems of quantum mechanical objects behave is becoming extremely important, because a quantum computer is a device which is built out of qubits. So remember, a qubit, an example would be an electron, which has this property that when you make an observation of the spin, let's say, of this electron, it behaves like a coin. It can be up or down, heads or tails, however you want to describe it. But that thing can also exist in a superposition, a combination of these things, and it's a perfectly valid configuration. And you use that. That's the kind of property that you use in building a quantum computer. You can also then ask the question, well, what happens if I get another one, two electrons together? These can be in what's called an entangled state. So then you have a much richer structure of this physical system. So an example of an entangled state, a very famous thing called a Bell state, would be where you set these things up. So the system of these two qubits, let's say they're up and down, these spins, right? So I can have the state up, down, plus, down, up, like that. A complete description of this state, up, down, plus, down, up. What does that mean? So let's say I take one of these electrons and I separate them. It's a very famous paper written by Einstein, Podolsky and Rosen that first considered this in the 1930s, and they get very upset by the behaviour. So we've got a system, a state, and it's up, down, plus, down, up, let's say. And I separate these electrons. I take one to, let's say, to Pluto, and leave one on planet Earth, right? And then, so what's the description of this thing in that state? Well, it's got, in the way I described it, there's a 50-50 chance that when I make a measurement of this electron, the up or downness of it, then there's a 50-50 chance it'll be either up or down. And the same for the other one. That's what that state means. But if it's up, down, plus, down, up, then it means that if I make a measurement of that one, if I say, well, okay, I know what that is, it's up. The other one has to be down. Up, down, or down, up. It can't be up as well. Same for the other one. If I go to Pluto and have a look at this one and it's down, then this one definitely is up, right? So